The strangest thing about the universe is not that it is violent or cold or unimaginably large. It is that by every simple expectation, it should already be full of life we can see, hear, or at least infer, and yet the sky remains silent. And one of the most unsettling possibilities is that the silence is not an accident at all, but a warning. This matters because the question hiding inside that silence is not just whether aliens exist. It is whether something in the structure of reality, biology, intelligence, or survival makes cosmic civilizations rare, brief, hidden, or doomed. By the end of this, you will understand why the Fermi Paradox is not just a fun science puzzle, but a deep and disturbing clue about what kind of universe we may actually live in. And if you genuinely enjoy this kind of deep space storytelling, take a second to like the video and subscribe. It really does help the channel keep making these long, careful journeys through the cosmos. And let me know in the comments where you are watching from. And one more thing. If intelligent life exists somewhere out there, do you think it is more likely to be hiding, expanding, or already gone? Now, with that in mind, let us step into one of the darkest ideas in modern astronomy. Imagine a quiet lunch conversation in the middle of the 20th century, when nuclear physics was still young. The space age had barely begun, and the Milky Way had not yet revealed even a single confirmed planet around another star. One simple question was asked. If the universe is so old and life has had so much time, where is everybody? Why does a galaxy filled with hundreds of billions of stars look so empty? Why has no probe, no beacon, no engineered structure, no unmistakable sign crossed our path? If life can arise and intelligence can persist, should the galaxy not already bear the fingerprints of someone? And if it does not, what does that absence say about life, about intelligence, and possibly about us? The Fermi Paradox begins with a mismatch between two things that both seem reasonable. On one side, the galaxy is vast, ancient, and rich with opportunity. On the other side, our observations reveal nothing that clearly points to a technological civilization beyond Earth. Not no life, not even no intelligent life. The paradox is narrower and sharper than that. It is the tension between what seems statistically plausible and what we actually see, which so far is silence. To feel the force of that silence, we need to start with scale. The Milky Way is around 100,000 light-years across. It contains hundreds of billions of stars. Around many of those stars we now know there are planets. That alone changed the conversation dramatically over the last few decades. In the 20th century, exoplanets were speculation. Today, they are a catalogue. Thousands have been found, and that is just from the tiny fraction we are capable of detecting. Planets are not rare decorations. They seem to be a normal part of star formation. Some of those planets sit in what is often called the habitable zone, the rough distance from a star where liquid water could exist on a rocky surface. That does not mean such worlds are Earth-like. Habitability is more complicated than one orbital distance. Atmosphere matters. Magnetic fields matter. Geological activity matters. The star itself matters. A planet can be in the habitable zone and still be a hellscape. But the broader point remains. The galaxy contains an enormous number of places where chemistry, complexity, and time may have had room to work. and time is the real engine of the paradox. Earth is about 4.5 billion years old. Our species has been around for only a tiny sliver of that. Radio technology, the kind that could produce a signal detectable across interstellar distances, is barely more than a century old. Spacefaring civilization, in any meaningful sense, is younger still. We are cosmic newborns. Yet the galaxy is old enough that many stars, and their planets, formed billions of years before the Sun. If even a small fraction of those earlier worlds gave rise to life, and if even a smaller fraction produced intelligence and technology, Andy, some civilizations could in principle have had an immense head start. This is where the paradox becomes hard to shrug off. You do not need faster-than-light travel. You do not need godlike super-aliens crossing the universe in an afternoon. Even slow expansion across the galaxy, if sustained over millions of years, could in theory spread a civilization or its machines remarkably far. 1,000,000 years sounds immense to us. On human scales, it is almost incomprehensible. But on galactic timescales, it is short. 10 million years is a blink to a galaxy more than 10 billion years old. Even sending self-replicating probes, machines that harvest local material to make copies of themselves and continue outward, could spread widely without violating known physics. Slow, patient, wave-like expansion could still leave traces. So where are those traces? No giant energy-harvesting structures plainly visible. No obvious engineered reshaping of stars. No confirmed alien probes parked in the solar system. No undeniable messages. No ruins on Mars with suspicious right angles and convenient subtitles. The night sky, for all its splendor, does not yet look inhabited. This question has produced a long list of possible answers. Maybe life is extremely rare. Maybe intelligence is rare. Maybe technological civilization is unstable. Maybe interstellar travel is too hard. Maybe they are here but unrecognized. Maybe they are not interested. Maybe we have not looked long enough. Maybe advanced civilizations become digital and inward-looking. Maybe they migrate to colder outer regions to compute more efficiently. Maybe they communicate in ways we do not know how to detect. Maybe we are early, maybe we are alone. Many of those possibilities are strange. Some are hopeful, some are melancholy. A few are truly dark, and the darker answers are not necessarily dramatic in the movie sense. They are dark because they imply that something about life and intelligence systematically fails. Something filters worlds like ours out before they become old, stable, and visible. That idea is often called the Great Filter. It is one of the most haunting concepts attached to the Fermi Paradox. Imagine the path from dead chemistry to a galaxy-spanning civilization as a series of steps. A planet forms. Complex molecules arise. Life begins. Cells become more complex. Multicellular organisms appear. Intelligence evolves. Tool use becomes technology. Technology becomes industry. Industry becomes a planetary civilization. And a planetary civilization survives its own power and reaches the stars. If the galaxy appears silent, then maybe one or more of those steps is extremely improbable or extremely dangerous. The first question is comforting and terrifying at the same time. Is the Great Filter behind us or ahead of us? If it is behind us, then perhaps the emergence of complex life was unbelievably rare, and we are precious winners of a cosmic lottery. If it is ahead of us, then perhaps many worlds produce intelligence, and many intelligent species reach a stage like ours, only to disappear before they become visible across the galaxy. That is the darker answer. Not that the universe lacks life, but that civilizations tend to die. Not once in a while, but reliably enough to keep the sky quiet. Before we go deeper into that darkness, it is worth remembering that silence is not evidence of one specific cause. It is only a clue. The Fermi Paradox is a framework for inference, not a solved mystery. We do not yet know how easy life is, how common intelligence is, how long technological civilizations last, or what signatures we should expect from advanced beings. The danger comes when one unknown is casually replaced by confidence. Still, some patterns are hard to ignore. Let us start with life itself. For a long time, people assumed that once a planet cools down and has water, life may naturally emerge. We still do not know. On Earth, life appeared relatively early in the planet's history, perhaps within a few 100 million years after conditions stabilized enough to allow it. Some researchers interpret that as a hint that life may emerge readily under the right conditions. Others caution that we are working from a sample size of 1. If life had taken much longer here, we would not be around to notice. That is an observation bias so severe it can mislead intuition completely. Then there is the leap from simple life to complex life. For most of Earth's history, life remained microscopic. For billions of years, our planet was ruled not by forests, animals, or civilizations, but by microbes. Tiny, resilient, wildly successful. Complex multicellular life arrived much later. Intelligence capable of building radios arrived much later still. If Earth is any guide, life beginning is not the same as life becoming interesting to telescopes. Even on Earth, some of the key transitions may have been extraordinarily contingent. Complex cells, the kind all plants and animals are made of, seem to have arisen through an ancient merger between simpler cells. One cell took up residence inside another and became what we now call mitochondria, the energy-producing structures inside our cells. That symbiotic event may have been rare, maybe even a one-off. If so, planets full of life could still remain forever microbial. A galaxy teeming with slime would be biologically rich and technologically silent. That already softens the paradox. Maybe there is life everywhere, and almost all of it is bacteria-like. But even that answer leaves an ache. Because once you grant enough planets, enough time, and enough evolutionary experimentation, then it feels hard to believe that intelligence would happen exactly once and nowhere else in the Milky Way. Not impossible, just startling. So attention turns to intelligence and civilization. Intelligence is not a ladder with a built-in destination. Evolution does not aim at science fiction. It selects for what works locally and temporarily. Dinosaurs ruled Earth for far longer than humans have existed, and none built radio telescopes. Intelligence of the humankind may be useful under certain pressures, but it may not be favored often. Brains are expensive. They consume energy. They require long development, social structures, and environmental niches where flexible problem-solving outcompetes simpler strategies. And even if intelligence evolves, technology is another step entirely. Dolphins are intelligent. Octopuses are astonishingly capable, and neither is likely to smelt iron or launch satellites, partly because their environments and body plans make cumulative industrial culture difficult. Fire matters, Hands matter. Memory preserved across generations matters. Stable societies matter. Access to concentrated energy matters. The path to a technological civilization may require a very unusual package of conditions, not just one lucky mutation. Still, let us say it happens. Let us say many worlds produce toolsing, curious, socially organized beings. The next dark possibility is that most never remain stable long enough to matter. Civilizations may be intrinsically brief. There is a brutal logic to that idea. The same intelligence that lets a species reshape its world also gives it the ability to damage its world faster than natural selection can correct it. Technology multiplies power. At first, that power feels like liberation. Fire, agriculture, engines, medicine, electricity, chemistry, computing, nuclear physics. Each step solves problems and creates new capacities. But power without maturity can become a trap. A civilization may become most dangerous to itself precisely when it becomes most capable. This is not abstract. In little more than a century, humanity learned to harness fossil energy, split the atom, alter the atmosphere, engineer pathogens, connect billions of minds through fragile digital systems, and place complex infrastructure between itself and ecological collapse. Our achievements are extraordinary. So is our ability to produce global-scale risk. We are, in a sense, experimenting with civilizational survivability in real time. That does not mean doom is inevitable. It means the filter, if it exists, could take forms we instantly recognize. Nuclear war is the obvious example, though not the only one. A full-scale exchange would not necessarily sterilize Earth, but it could collapse global civilization, devastate ecosystems, and permanently alter the trajectory of technological development. Some societies might recover, some might not. The point is not that one war ends life forever. The point is that the ladder upward may be fragile. Civilizations might climb partway, stumble, and vanish before they leave durable interstellar footprints. Environmental collapse is another candidate. A civilization dependent on rapid resource extraction may undermine the very systems that support it. Climate instability, biodiversity loss, soil exhaustion, freshwater disruption, ocean acidification, cascading feedbacks, and none of these are science fiction. A species smart enough to build industry may still fail at long-term stewardship, especially if evolution equipped it for short-term competition rather than planetary foresight. Then there is biotechnology. As knowledge spreads, destructive capacity no longer remains confined to states and armies. The tools for manipulating life become cheaper, more powerful, and more accessible. A civilization may enter an era in which tiny groups, or even individuals, can unleash disasters once possible only for governments. That shifts risk in a profound way. A species may not need one giant war to fail. It may face a statistical wall where, given enough time and enough actors, some catastrophic misuse becomes likely. Artificial intelligence appears in modern versions of the filter for a similar reason. Not because machines becoming conscious is required, but because systems more capable than their creators may be deployed in military, economic, or infrastructure contexts before safety and control are fully solved. A civilization racing ahead under competition might build tools it cannot govern. Again, this is not a prediction. It is one more example of a dangerous threshold where intelligence produces destabilizing power faster than wisdom evolves. There are also less dramatic filters: social fragmentation, permanent authoritarian lock-in, cultural exhaustion, declining capacity to coordinate at planetary scale. A civilization does not need to explode to disappear from the cosmic stage. It may simply stop growing, stop exploring, and retreat into survival mode for millennia. From far away, a stalled world is almost as silent as a dead one. But perhaps the darkest answers are not internal. Perhaps the universe itself is more hostile than our day-to-day lives make it seem. Earth feels stable because most disasters unfold on human timescales we can comprehend and manage. The cosmos does not care about those scales. Supernovae, gamma-ray bursts, asteroid impacts, stellar flares, black hole jets, gravitational disruption, atmospheric stripping, long-term orbital chaos, nearby radiation events. Space is not merely empty. It is active, and sometimes violently so. Consider gamma-ray bursts, among the most energetic explosions known. They are thought to occur when massive stars collapse, or when certain dense stellar remnants merge, producing intense, narrow beams of radiation. If one were pointed directly at a planet from relatively close range, it could damage the atmosphere severely, deplete ozone, and expose the surface to harmful ultraviolet radiation from the host star. Such events are rare in any one place, but in a galaxy with vast time to work, rare things happen. Some researchers have asked whether mass extinctions or sterilizing near misses elsewhere could act as resets, periodically pruning the rise of complex life. Or take red dwarf stars, the most common stars in the galaxy. Many of the potentially habitable planets we are likely to find orbit these small, cool stars because their habitable zones are close in, making detection easier. But red dwarfs can be tempestuous, especially when young. Powerful flares and stellar winds may strip atmospheres or bombard surfaces with radiation. A planet in the habitable zone of a red dwarf may also be tidally locked, with one side always facing the star. That does not automatically make it uninhabitable, but it complicates the picture. The stars most abundant in the galaxy may not be the kindest homes for long, stable biospheres. Even our location may matter more than we like to think. The galaxy is not uniform. The dense inner regions have more stars packed close together, which increases the chance of nearby catastrophic events and gravitational disturbances. The outer regions may have fewer heavy elements needed for rocky planets and chemistry-rich environments. Some researchers speak of a galactic habitable zone, a broad region where conditions may be more favorable for complex life over long periods. If that is real, then the number of truly suitable worlds could be far smaller than raw planet counts suggest. And then there are the invisible predators of time itself. Stars brighten as they age, planetary climates drift, magnetic fields weaken, plate tectonics may stop, atmospheres leak away, oceans can be lost. Habitability is not a permanent label. It is a moving window, and on many worlds that window may be narrow. Life may begin, struggle upward, and run out of time before intelligence has a chance. Now let us widen the lens again. The Fermi Paradox becomes darker still when we consider not just extinction, but strategic silence. One possibility is that advanced civilizations exist, but the universe rewards hiding. This is often called the dark forest idea, borrowed from a science fiction metaphor, but its emotional power comes from something older and simpler. Imagine a forest at night. Every creature is listening. No one knows who else is out there. No one knows who is harmless, who is hungry, or who has already decided that caution is weakness. In such a forest, announcing your position may be the last mistake you make. Applied to the cosmos, the idea goes like this. Civilizations cannot easily know the intentions or future behavior of distant others. Distances are enormous, communication is slow, and technological disparities could be vast. A civilization that remains quiet is hard to find. One that broadcasts is easier to locate. If even a small fraction of advanced civilizations are aggressive, paranoid, or simply unwilling to tolerate potential future threats, then silence may be the winning strategy. The galaxy appears quiet, not because it is empty, but because everyone who understands the rules has learned to whisper. This is not established science. It is a speculative solution, and a severe one. There are strong objections. Interstellar warfare may be impractical. Detecting life-bearing planets is already becoming possible through astronomy, so total concealment may be impossible anyway. Launching attacks across light years is technologically and strategically difficult. And civilizations capable of such feats may have motives we cannot meaningfully predict. The dark forest is not a conclusion. It is a thought experiment about game theory under extreme uncertainty. But it is disturbing because it reveals another way silence could emerge naturally, not through death, but through fear. There is a related possibility that is less cinematic and in some ways more plausible. Advanced civilizations may avoid obvious, energetic, attention-grabbing behavior simply because efficiency improves with maturity. The civilization that lit up its sky with wasteful radio transmissions and giant visible engineering may be an adolescent phase. Later, power use becomes cleaner, tighter, more computational, perhaps shifted into forms we would struggle to detect. If so, our search methods may be tuned to the noisy middle stage, like trying to detect modern fiber optic civilization by listening for horse carts. This leads to a subtle point in the paradox. We often assume that advanced civilizations should be obvious. But obvious to whom, and by what standard? And human technology leaks certain signatures because of the way we built it. Another species may not use radio in the same way for long. It may communicate with tightly beamed signals, optical systems, neutrinos, quantum effects that do not violate physics, but do evade our current detection habits or methods we have not imagined. It may choose low-temperature computation in outer planetary systems, where waste heat is minimized. It may upload minds into compact hardware and need very little visible infrastructure. A civilization can be powerful without being flamboyant. Even so, total invisibility is hard. Physics leaves traces. Energy use generates waste heat. Large-scale engineering changes orbits, spectra, light curves. Astroengineering on stellar scales should in principle produce anomalies. Astronomers have looked for some of these signatures, including unusual dimming patterns around stars and excess infrared emission that might indicate large energy harvesting structures. So far, nothing compelling has emerged. Some odd cases have appeared, drawn headlines, and then found more ordinary explanations in dust, debris, or natural variability. The universe is very good at making weird natural things that look exciting for a while. That natural weirdness matters. Another reason the paradox remains unsolved is that astronomy is hard. We observe from one small world through limited instruments across immense distances. Our search has barely begun. The volume of parameter space is staggering. Different wavelengths, different timescales, different signal types, different locations, different assumptions about intent and technology. If the ocean were the galaxy, our SETI efforts, the search for extraterrestrial intelligence, might be compared not even to dipping a glass into it, but to testing a few drops from a sea breeze and wondering why we have not found whales. That comparison is imprecise, but the humility behind it is justified. We have not looked for long. We have not looked everywhere. We have not looked with complete sensitivity. There is no contradiction in saying the silence is troubling, and also that our sample is poor. Both can be true at once. Still, the darker possibilities return because of one stubborn fact. The galaxy is old enough that even improbable things have had many chances, and some processes, once begun, should spread or persist. If there are civilizations that build long-lived probes, or monuments, or automated archives, one might expect at least a few relics. The absence of clear artifacts in our own solar system has inspired another line of thought. Maybe we should search not just the stars, but our celestial backyard. This idea sounds almost mischievous at first. Why obsess over signals from distant suns if an ancient robotic probe could be tucked away on the moon, on an asteroid, in a stable orbit, or lurking among the gravitational balance points of the Earth-Moon system? Such places, called Lagrange points, are regions where gravitational forces can create relatively stable arrangements. They are natural parking spots. A patient civilization interested in observation might prefer sending autonomous watchers rather than dramatic fleets. Some scientists have proposed systematic searches for unusual objects in such locations, not because there is evidence of alien probes, but because the cost of checking is low compared to the significance of finding one. Again, no confirmed artifact has been found, but the suggestion itself reshapes the paradox. Maybe visibility is not the default. Maybe the galaxy is not a city lit in neon, but an archive of subtle traces. And yet, if we keep following the logic of dark answers, we arrive at something even more unsettling than war, disaster, or fear. We arrive at the possibility that intelligence contains a built-in instability. Not this civilization or that one, not one accident or another, but something structural. Think about what technology does to evolutionary timescales. Biological evolution is slow. Cultural and technological evolution is fast. Once a species reaches a certain threshold, it begins changing its environment, its social systems, and eventually itself far faster than genes can adapt. The species becomes detached from the pace that produced it. Ancient instincts drive modern power. Territoriality, status competition, tribal identity, impulsiveness, reward systems built for scarcity, all operating inside a civilization with nuclear weapons, algorithmic persuasion, synthetic biology, and planetary scale infrastructure. That mismatch may be more than a historical inconvenience. It may be a universal trap. In that view, intelligence is not automatically a stable adaptation. It is a volatile transitional state. It can generate extraordinary creativity, but also existential risk. It can unlock science, art, medicine, and cosmic awareness, odds to us, while simultaneously destabilizing the ecological and psychological foundations that made it possible. A civilization may be brightest just before it burns through its margin for error. There is a haunting elegance to this possibility. It would explain why the universe can produce intelligence and still remain silent. Civilizations flare briefly. They become detectable for a few centuries or millennia. Then they collapse, transform into something undetectable, or destroy themselves. The overlap between two such windows across interstellar distances could be tiny. The galaxy may not be empty. It may be full of missed connections, civilizations separated not only by space, but by time. Imagine two worlds on opposite sides of the Milky Way. One broadcasts for 2,000 years and then goes dark, and another develops radio 100,000 years later. Both produced intelligence. Neither ever knows the other existed. In a galaxy billions of years old, this may be common. Not a grand conversation, but isolated sparks. This temporal angle softens the paradox in one way and darkens it in another. It means silence does not require that every civilization dies violently. Many might simply be too brief, too early, too late, too far apart. But the deeper darkness remains. Why are they brief? One answer is adaptation into forms that do not care about expansion. Popular imagination often assumes advanced life will spread aggressively, colonize stars, and reshape the galaxy. But perhaps that is projection. Maybe expansion is costly, unnecessary, or philosophically uninteresting to mature civilizations. A species may turn inward and into virtual worlds or dense computational habitats, extracting meaning from inner complexity rather than outer empire. If such societies use limited energy, emit little waste, and avoid conspicuous engineering, they could be almost invisible. This is sometimes presented as a hopeful answer because it replaces extinction with transcendence. But it carries its own unease. A universe filled with silent, inward civilizations is a universe where intelligence does not bloom outward into shared, visible culture. The stars remain dark not because nothing survived, but because survival itself leads away from the sky. And then there is the possibility that we are asking the wrong observational question entirely. We seek civilization as though it should look like more of us, only bigger. Radios, megastructures, probes, industrial atmospheres, engineered light. But truly advanced intelligence might blur the distinction between biology and machine, or between individual and environment. It could exist in forms so alien that our categories fail. We may be searching for cities and finding weather, searching for messages and staring through artifacts we do not recognize as artificial. This sounds like an escape hatch, and it can become one if used carelessly. They are too advanced to detect is not a scientific explanation by itself. But it is fair to admit that our expectations are human-shaped. The universe may not reward those expectations. Still, there are reasons many researchers keep returning to filters and hazards rather than pure unknowability. One reason is that difficult technology does not erase simple physics. Another is that survival across deep time really is hard. Earth has endured mass extinctions, asteroid impacts, supervolcanoes, ice ages, shifting continents, and changing atmospheres. Complex life persisted, but not smoothly. If our own planet has repeatedly approached catastrophe without intelligent opponents, then worlds elsewhere may face similar or worse instability. A civilization must survive not just itself, but geology, climate, astronomy, and chance. There is also a selection effect that quietly sharpens the issue. We are observing the universe from a world that has not yet obviously failed. Of course we are. failed civilizations do not ask cosmological questions. This means our perspective is inherently biased towards survivorship. We should be cautious about assuming our path is typical simply because it is the only one we know. The cemetery can be invisible to the living. Now, let us bring in one of the classic tools people use to think about this: the Drake equation. It is not really an equation in the predictive sense. It is more like a framework for organizing ignorance. It breaks the number of detectable civilizations in the galaxy into factors: the rate of star formation, the fraction of stars with planets, the number of potentially habitable planets, the fraction where life emerges, the fraction where intelligence evolves, the fraction that develop detectable technology, and the length of time they remain detectable. Some of those terms are now better constrained than they used to be. We know planets are common. We have growing insight into how many rocky worlds exist. But the biological and sociological terms remain deeply uncertain. That uncertainty allows both optimism and pessimism. If life arises easily and civilizations last long, the galaxy should be busy. If life is hard, intelligence is rare, or detectable phases are brief, then silence becomes less surprising. The darkest answer often hides in the last term: lifespan. Even if technological civilizations are not terribly rare in total number across cosmic history, if each remains detectable for only a short time, the number existing right now may be very small. The Fermi Paradox becomes not "where is everybody forever?" but "why does almost nobody stay visible for long?" That framing brings us closer to the emotional core of the problem. The paradox is not only about aliens, it is about longevity. It asks whether intelligence is a durable feature of the universe, or a fragile flash, whether minds that awaken under the stars tend to grow into cosmic participants or brief accidents, whether knowledge leads to survival, or whether knowledge mostly increases the ways to fail. There is a temptation here to become melodramatic, as if the silence proves doom. It does not. We do not know enough to justify despair. It is possible that the filter is mostly behind us. It is possible that microbial life is common, but complex life is astonishingly rare. It is possible that our search methods are crude and our expectations provincial. It is possible that the first clear detection will come not from a dramatic beacon, but from subtle atmospheric chemistry on an exoplanet, a pattern in starlight, or a strange object in our own solar system. In fact, one of the most exciting developments in astronomy is that we are beginning to probe exoplanet atmospheres. When a planet passes in front of its star, a tiny fraction of starlight filters through the planet's atmosphere, allowing us to infer some of its components. This is difficult and limited, but improving. In the future, astronomers hope to identify biosignatures, signs that life may be altering an atmosphere, such as combinations of gases that are hard to maintain without biology. Even more ambitious would be technosignatures, signs of technology, like unusual industrial chemicals or artificial night-side illumination, though those are much harder to detect. The point is that the silence is no longer being faced with empty hands. We are learning how to listen better. Yet better listening may deepen the mystery. Suppose we eventually find many worlds with simple life, but none with clear civilization. That would push the filter toward complexity or intelligence. Suppose we find many biospheres and occasional technosignatures that appear and vanish. That would support the brief window idea. Suppose we find nothing, not even life, on world after world. Then the origin of life itself may be the rare miracle. Every future discovery reshapes the darkness differently. There is another, more philosophical dark answer that deserves attention because it changes the emotional texture of the paradox. Maybe intelligence naturally destroys the illusion that expansion matters. We imagine star-faring civilizations because movement and growth define our history. But perhaps once a species understands consciousness, suffering, ecology, and thermodynamics deeply enough, it becomes more cautious, less imperial, less visible. The galaxy is not colonized because wisdom puts brakes on power. In that case, silence would not signal doom or fear, but restraint. That is not exactly dark. Yet from a human perspective, it can feel eerie. A quiet galaxy of wise civilizations choosing non-expansion would look observationally much like a dead galaxy. Meaning can hide behind the same silence as catastrophe. That is one reason the Fermi Paradox resists simple resolution. Different universes can produce the same sky. Still, if we are honest, some answers weigh more heavily because they line up with what we know about risk, competition, and finite worlds. Consider how many planets may never achieve long-term stability because their host stars behave badly. Consider how many biospheres may remain microbial. Consider how many intelligent species may emerge in environments that do not permit industry. Consider how many technological civilizations may ignite and then destroy themselves, or withdraw, or be erased by impacts, radiation, or internal collapse. Multiply moderate improbabilities across many steps, and the final outcome may be rarity without requiring any single impossible hurdle. The darker answer, then, may not be one dramatic killer. It may be accumulation, a gauntlet of filters, a universe where life has many chances to start and even more chances to fail. That is a colder picture than a single great filter, because it means there may be no one monster at the end of the path, no one mistake to avoid. Just repeated vulnerability. A little too much radiation here, a missed symbiosis there, an unstable climate, a bad moon, a tidal lock, a poor magnetic field, a mass extinction at the wrong time, a species that evolves intelligence but not cooperation, a civilization that masters energy before governance, a weapon developed in a moment of fear, an algorithmic arms race, a biosphere pushed past recovery, a nearby supernova, a chain of bad timing across billions of years. Not cosmic drama, cosmic attrition, and attrition is perhaps the darkest possibility of all, because it offers no villain, only indifference. But the story does not end in indifference, because the paradox also reveals something extraordinary. Against whatever odds existed, here we are. A technological species on a small, rocky world, orbiting an ordinary star in a quiet arm of one galaxy among hundreds of billions, are looking up and noticing the silence. The universe produced atoms, stars, planets, chemistry, cells, evolution, minds, language, science, telescopes, radio arrays, and the very question of whether anyone else has done the same. That alone is astonishing. There is a tendency to treat the Fermi Paradox as though it were purely discouraging. In truth, it sharpens wonder by adding seriousness to it. If the universe is full of danger, then every stable world becomes more precious. If intelligence is fragile, then every library, observatory, and spacecraft matters more. If civilizations often fail, then survival is not automatic, and curiosity is not trivial. It becomes a rare flame worth tending carefully. And there is something else. The silence may be temporary. Not because the galaxy is waiting for us personally, but because scientific history is full of transitions from ignorance to revelation. Before microscopes, a drop of water looked empty. Before radio astronomy, the sky looked quieter. Before exoplanet detection, other worlds were largely philosophical. We stand at another threshold now. Telescopes are sharpening. Data is accumulating. Methods are diversifying. We are searching not only for messages, but for chemistry, heat, structure, and anomalies. The paradox remains, but its edges are becoming testable, even if the answer turns out to be dark, knowing it would change us. If life is rare, then Earth is more valuable than ever. If complex life is rare, then biology is more precious. If intelligence is common but unstable, then long-term survival becomes the central challenge of any civilization that wakes up. The silence above us may not merely be an astronomical puzzle. It may be a mirror held up to the future. And perhaps that is why the Fermi Paradox grips people so deeply. It compresses the biggest scales into the most personal stakes. It begins with stars and ends with choices. It asks what the universe allows, but also what intelligence does with power once it has it. It forces us to look at the Milky Way not just as scenery, but as evidence. When you see the galaxy on a dark night, it is easy to imagine it as full in the cheerful sense, full of destinations, full of civilizations, full of voices waiting just beyond our reach. It may be, but the harder possibility is that it is full of absences. Worlds where life never began, worlds where it never advanced, worlds where it flourished and died, worlds that learned to hide, worlds that flickered and went silent before any neighbor could notice. A billion chances, and still a dark sky. If that is true, then the awe of the universe changes flavor. It becomes less like entering a crowded cosmic city, and more like walking through the ruins of possibilities. Not literal ruins we can point to, at least not yet, but statistical ruins. Missing civilizations, lost branches of what might have been. The night becomes beautiful in a more sober way. And yet sober wonder may be the deepest kind. Because in that silence, one world has begun to listen. One species, however flawed, has started to understand stars, planets, evolution, and the hazards written into matter and time. We may be early, we may be rare, we may be one brief spark among many others that came and went unseen. We do not know. But the fact that we can ask is itself part of the cosmic story. The Fermi Paradox may have a darker answer than we thought, because the universe may not simply fail to produce life. It may produce life often enough to tempt hope, intelligence often enough to tease possibility, and survival rarely enough to keep the stars quiet. That is not a proven conclusion. It is a warning embedded in uncertainty. The silence might mean we are alone. It might mean others are hidden. Or it might mean that becoming a lasting civilization is one of the hardest things matter can do. If so, then the paradox is not only out there in the galaxy, it is here, in every decision that affects whether intelligence on this planet remains a brief chemical event or becomes something that endures. The dark answer is not that the universe is evil. No, it is that the universe may be full of thresholds, and most who approach them do not pass through. That possibility leaves us with a strange kind of hope, one that is more mature than optimism, hope rooted not in guaranteed success, but in the knowledge that survival, wisdom, and expansion of understanding may be rare and therefore meaningful. The night sky does not owe us company, but it does offer a question, and maybe also a challenge. So the next time you look up at the Milky Way, remember what makes the silence unsettling. In a galaxy this old, somebody should have been visible by now. If nobody is, then either life is unimaginably rare, intelligence is usually short-lived, advanced civilizations choose invisibility, or reality is stranger than our current models can capture. Any of those possibilities would change how we see our place in the cosmos. And maybe that is the final twist. The Fermi Paradox is dark not because it closes the universe, but because it opens it in directions we would rather avoid. It asks us to consider that the stars are not silent by accident, that there may be reasons written into biology, physics, time, and survival itself. Reasons that make the universe not less awe-inspiring, but more severe, more mysterious, and far more consequential than it first appears. Thank you for being here and taking this journey with me. If the cosmos is quiet for a reason, then understanding that reason may be one of the most important discoveries our species ever makes. Until next time, keep looking up and keep listening to the silence.